Alright students, so today we're talking about complex numbers in trig form, also known as polar form. Specifically how to convert a complex number to trig form from rectangular form and vice versa. So going back and forth, we're going to look at some theory, then we'll do some practice problems. So let's go ahead and say we have a complex number z equals a plus bi. Now this is specifically called a complex number in rectangular form. We can write that as an ordered pair, a plus bi, and then we could graph it. So just putting the real part in the first position, the imaginary part there, and what we would normally put as the y position, the second position. And then when we draw our axes, instead of x and y, we're going to have the real axis and the imaginary axis. And then we just go to the right or to the left, then as many units a, up or down, b, and then we plot our point, and that is our complex number graphed on a real and imaginary axis. And since that's our point, we could talk about the magnitude of z, the magnitude of that complex number. And since we've got a magnitude, we could talk about the direction as it relates to the positive, I would normally say x-axis, but positive real axis. All right, you can see we've got those real and imaginary components. So we can find the magnitude of that complex number. Yep, you guessed it, square root of the sum of the squares. Good old Pythagorean theorem. That's called the magnitude of the complex number. And a little hard time drawing the number symbol there. And theta is the inverse tangent of b over a. That's the direction. That's the angle of the complex number. Now, in reality, you probably want to put absolute value there, absolute value bars, and then or magnitude bars, however you want to call them there, and then call this angle inside the triangle the reference angle, and then use your knowledge of which quadrant you're in to figure out the exact angle. And we'll talk about it, but we know, and we've seen this formula many times with vectors and with polar coordinates and whatnot. So yeah, this sounds a lot like the stuff that you do in vectors or polar coordinates and polar numbers. So yeah, lots of similarities there. A couple of things to note along those lines, since we're thinking about it, that the cosine of that angle would be adjacent over hypotenuse. So that would be a, the real part, over the magnitude. If we solve that for a, multiply both sides by magnitude of z, we have a equals magnitude of z cosine theta. Along the same lines, if we think about the sine of this angle theta, then that would be b, the opposite side of that triangle over the hypotenuse, which is the magnitude of z. Solving for b, multiplying both sides by magnitude z, we get b equals z cosine theta. Once again, look familiar? Magnitude sine theta, magnitude cosine theta. Yeah, we're real happy about that. So as a result, when we have the complex number a plus bi, we can substitute for a, magnitude of z cosine theta, substitute for b, magnitude of z sine theta. We notice that both of those terms have a z, so we can factor that out. So we have magnitude of z, open parentheses, cosine theta plus I sine theta. Hooray! So sometimes you'll see r out here, r, and then the parentheses cosine theta plus I sine theta. Just sort of depends on the context here. This form is a complex number in trigonometric form. Also, it's sometimes called polar form. And sometimes we get really lazy and don't want to write all those parentheses and stuff, and we just say the magnitude cis theta, because that's really the major information, the magnitude and the direction or the angle there. So some examples would be like 5 cis 20 degrees or 3 cis pi over 6 or whatever, where obviously there's the magnitude, there's the angle. And as I mentioned before, there's a whole lot of similarities here. If you can go back and forth between this magnitude and angle and then the x and y components or whatever, you are really set in trig or pre-calculus or whatever. There's similarities between these operations between complex number in rectangular form and the complex number in trig form, where you've got the magnitude and the theta. Similar to with vectors, when if you have a plus b j form versus standard form, which once again magnitude and direction. If you've got a polar coordinate, versus a rectangular coordinate. The rectangular coordinate is going to have an x and y. The polar coordinate is going to have an r and theta. So anyway, lots of similarities there among everything here in this right column and the left column as well, and the process is exactly the same. If you're going from left to right, you're doing Pythagorean theorem and sine and cosine. If you're going from right to left, you're doing well, I guess hold on if you're going right to left, you're doing you're breaking that down, r cosine theta, inverse tangent, going the other way, doing tangent. Okay, let's get going here. This is a previous problem. Now this is our current problem. Plot the complex numbers -6 plus I and 3 minus 8i in the complex plane. You can look here in our graph. We have the real axis and the imaginary axis. So -6 on the real, that's kind of like the x, so there's -6. There's 1. Boom. That's the answer. That's how you plot that complex number. That wasn't too hard, was it now? 3 minus 8i. 3 is the real part, so we'll go over 3, 8, or minus 8, right down there. That's our complex number. We're happy. Let's move on. This problem says write each complex number in standard or rectangular form. Give exact values in your answers, not decimal approximations. So here we have the sissy form, 2 cosine 7 pi over 6 plus I sine 7 pi over 6. So remember, 2 is the magnitude. There's our angle there. So what we're going to do is just good old distribution. So 2 cosine 7 pi over 6 plus 2 times I times sine 7 pi over 6. So the way that we evaluate those cosines and sines is we go over to our unit circle, find 7 pi over 6. There it is right down here, -3 root 2 and -1/2. So -3 root 2 for the cosine plus 2 times I, and what was that one again? Oh, -1/2 for the y value, so -1/2. And now we just do a little bit of arithmetic. 2's will cancel, so we have -√3. That 2 and that 2 cancel, so we have minus I. And we're done with this first part, converting this complex number that is currently in trig form, or polar form, and converted it into rectangular form. So, hooray for that. Same kind of thing, but this one just has our angle in degrees rather than radians. No big deal. We'll follow that same process. Distribute that 3. So we have 3 cosine 135 degrees plus I times 3 times sine 135. Go to our friendly unit circle. 135 has -√2 root 2 and positive root 2 over 2. So we'll write 3 times -√2 over 2 plus I times 3 times root 2 over 2. And so that's just going to be -3 root 2 over 2 plus 3 root 2 over 2 I. That's the standard way we want to write it, with the number in front of the I. That looks great. Okay, let's go the other way. We have a complex number. This is in rectangular form, where we have an A plus BI. And we want to write that in trig form. So we want to have that Z cosine plus I sine stuff. And according to these instructions, they want this angle to be in radians and between 0 and 2 pi, and that's indicating that they want an exact answer there. No big deal. Let's graph this number first, just to kind of get an idea about which quadrant we're in. So -3 minus 3i. So that's our x value, that's our y value. So we're like -3, -3, and I can't draw a triangle apparently. So that's theta ref. Let's just go ahead and draw that all over again. Okay, so that's not much better, but that's theta ref. There's -3, there's -3. Here's the magnitude. We know that the magnitude is equal to the square root of the sum of the squares, so that's going to be -3 squared, -3 squared. So 9 plus 9, 18, which is square root 9 times 2, so not square root of 3. 3 root 2, and that's our magnitude. Theta ref is inverse tangent -3 over 3, or -3. So that's inverse tangent of 1. So using the calculator, I put mine in degree mode because I like degrees more than radians, and that gave me 45 degrees. So that's my theta ref. My actual theta, as measured from the positive x-axis, we know is going to be 180 plus 45, which gives me 225 degrees. Go back to the unit circle because I can never have these things memorized. Maybe you will. 5 pi over 4. So my theta is equal to 5 pi over 4. I have my magnitude. I have my theta. So z is equal to 3 root 2 cis 5 pi over 4. If I want to write that in the more friendly, proper way, that's 3 root 2, open parentheses, cosine 5 pi over 4 plus I sine 5 pi over 4. There it is, our complex number in trig form, also known as polar form. Here's another one, just to give another example. Step 1, always graph it. There's our x value, 3 root 3. There's our y value, negative 3. We're going to draw that acute angle and label it as theta ref. So magnitude of the complex number is the square root of the sum of the squares. So that's square root of 3 root 3 squared plus negative 3 squared. So 3 squared is 9. Square root of 3 squared is 3. So we have 9 times 3 plus 9. So that's 36. Square root of that is 6. Theta ref is inverse tangent. The absolute value of 3 over, kind of run over room there. So theta ref is inverse tangent of 3 over 3 root 3. So using the calculator, I get 30 degrees, which tells me this is 30 degrees. Now if I think about what theta is, then using my brain I realize that that's going to be 360 all the way around here minus 30. So 330 degrees. If you need to reference that on the unit circle, that is 11 pi over 6. So we have our R value of 6, or magnitude of whatever, and theta 11 pi over 6. So we write this in expanded form here. 6 cosine 11 pi over 6 plus I sine 11 pi over 6. Last one, sometimes they're going to want you to round this or whatever. That's really not that big of a deal. It's the same kind of thing. Says write this complex number z equals -1 plus 4i in trig form. So still want the angle in radians in between 0 and 2 pi, but they want us to round it. So no exact answers. And I say no big deal. Still going to go back to our standard process of graphing it. -1 on the x, 4 for the y. So that puts us in the second quadrant with the theta ref right there. So the magnitude z is equal to the square root of the sum of the squares. So that's square root -1 squared plus 4 squared. So that's 1 plus 16, so square root of 17. And hooray, I'm just going to type that into the calculator, round that to the nearest hundredth. So my magnitude there is 4.12. Theta ref, inverse tangent, y over x. So 4 over 1. So I put my calculator in radian mode here because I'm already got to be in radians. So let's just not mess with doing the degrees to radians conversions ourselves. So theta ref is 1.32 in radians. Now if I think about it, I think that theta right here is equal to pi minus theta ref. Pi mean 180 degrees, or that all the way here to this side right here, and I'm going to subtract theta ref. So that's going to be, just using the calculator, 1.82 for my angle. So z in polar form, 4.12 cis 1.82. If I want to expand that, I can write 4.12 cosine 1.82 plus I sine 1.82. And there we go. That's that 1.82, just as a reminder, is in radians. All right, that's our problem. We have solved it and put everything into the nearest hundredth. Thanks for watching.